Hello and welcome to our lesson on exponential functions. So switching gears a little bit, everything so far has been exponential, either expressions or equations, and then some logs in there too. But now we're going to look at exponential functions. So it's still exponential in that we still have a variable exponent, but instead of just solving for that variable exponent or doing some rewriting, now we're going to have two variables in our equation, and we're going to try to be graphing the relationship between those two variables. Okay, so exponential functions still have variable exponents. So what makes a function exponential is the fact that the exponent is a variable. So for example, y equals x squared, not exponential. That's not a variable exponent, okay? That is a quadratic function. So we're looking for an exponent as a variable. And specifically, what we're going to see is something like y equals, let's take the letter b and raise it to the x power. So I put a variable in there for the base of that exponent because it can be almost any number, but we want the y equals to make this sort of a function, right? And then we want the x to be our exponent so that it's an exponential function. But then again, that base can be almost any number. What it can't be is 0. So b can't equal 0 because 0 raised to any power is going to be 0. And so what you would be graphing as a result is a linear function. And the same thing would happen if our base was 1. 1 raised to any power is going to be 1, and it would create a linear function on a graph. So for this to be an exponential function, we want some base that isn't 0, that isn't 1, any other number, to be raised to the power of x. That's going to be an exponential function. And the exponent, of course, can be any real number. Okay, we can plug whatever we want in for that exponent of x, which means you're going to see an unrestricted domain on our graph. So we're going to talk more about that in just a second. So I know we have technology that graphs for us, but so that we understand what's happening on the graph, we're going to graph a few of these the old-fashioned way by making a table. So we're going to graph by making a table. And let's start with y equals 2 to the x. So we can kind of consider this like a parent function because they're all going to behave like 2 to the x behaves. So y equals 2 to the x power. If I go to make a table and plug in this negative 2, if I put negative 2 right there, what is 2 to the negative second going to be? Well, 2 to the negative second, remember, is 1 over 2 to the positive second, and that makes that 1/4. So we're going to do with 1 over 4 here, and you could actually use your calculator to do that too if you wanted. How about 2 to the negative first? 2 to the negative first would be 1 over 2 to the positive first, which would make it 1 over 2, so a half. How about 2 raised to the power of 0? Well, anything to the power of 0 is going to be 1, so it's going to be a 1 there, and there, and there, and there. Anything raised to the power of 0 is 1. Okay, and then 2 to the first is easy. That's 2, and 2 squared, not so bad. That's going to be 4. So if we go to make this picture, and I'm going to color code, so I'm going to change that. When I go to make this picture, at negative 2, our graph is at a 4th, so it's not very far above the x-axis. And then at negative 1, we're at a half, so we're a little higher. And then 0, we're up to 1. And then 1, we're up to 2. And then 2 squared is going to make 4. So there's the graph starting to form. Now, what's going to happen as we continue? If we were to continue picking, let's say, bigger values of x, so 2 to the third would make 8, 2 to the fourth would make 16, 2 to the fifth is going to make 32. As we continue picking bigger values of x, so going along the x-axis here, the graph is going to start growing really fast, right? Again, 2 cubed is 8, 2 to the fourth is 16, and then we're just going to keep doubling here, and so this number is going to get really big really fast. So on this side of the graph, again, 2 cubed was 8. Like here, we're just going to start to grow really fast, okay? So it's going to get really steep. What's happening the other direction? Well, in the same way that these numbers are growing, the bottoms of the fractions are going to grow, right? 2 to the negative third will be 1 over 2 to the positive third. So it's going to be 1 over 8, and then 1 over 16, and then 1 over 32. So if the top of the fraction stays a 1, but the bottom continues to get bigger, what's happening is the value of the fraction is going to get smaller and smaller and smaller. In fact, it's going to get infinitely small, but because the top is always going to have a 1 there, we can't actually get to a value of 0. So as we go the other direction, just making a mess of my notes here, as we go to the other direction, the fraction's going to get smaller and smaller, which means we're going to get closer and closer to the x-axis, but we can't actually get to the x-axis. So there's going to be a barrier in the graph. Remember, we call those barriers asymptotes. So there's going to be a horizontal asymptote in that graph. Okay? So there's 2 to the x. Now let's compare that to 3 to the x. If I put in negative 2 here, 3 to the negative 2 would be 1 over 3 to the positive 2, which makes it 1 over 9. Put in a negative 1, then it's 1 over 3 to the first, which is 1/3. Anything to the power of 0 is 1. 3 to the first is 3, and 3 squared is going to make 9. So what's going to happen on this graph is it's going to look pretty similar, right? At negative 2, our graph is at a 1/9, so somewhere around here. And then we're at a 1/3. Maybe it's negligible difference there from what we can plot on the graph. At 0, we're at 1. That's exactly the same point. Anything raised to the power of 0 is 1. But then at 1, we're at 3. And then 3 squared is going to make 4, 8, 9. So because that base is bigger, right, because we have a base of 3 here, and we're tripling instead of a base of 2 here where we're doubling every time, the graph grows even faster. So it's a little steeper as we go this direction. Oops, I missed. It's steeper as we go this way, okay, but the shape of the graph is about the same, and then as we go this direction, the behavior is basically the same. Negligible difference there. So 3 to the x compared to 2 to the x, these graphs are behaving the same way. They cross the y-axis at the same spot. They both have a horizontal asymptote at 0. It's just that when that base got bigger, that graph got steeper. And so if we had a base of 10, it's going to be multiplied by 10 every time, so it's going to grow even faster. And so the bigger the base gets, the faster that's going to grow, but the behaviors will be the same. Okay? So when you're thinking about, when we think about a quadratic function, we think about a parabola. When we think about an exponential function, this is really the shape that we should be seeing, where we have this horizontal asymptote, and then we have this graph that's kind of flat, hits the y-axis at 1, and then starts to grow really fast, and faster if we have a bigger base. Okay? Now, what if instead of 2 to the x, we graph 1 over 2 to the x? So let's look at the next one. If I put a negative 2 in this time, if I have 1/2 and I raise it to the negative second, well, that's going to be 2 over 1 to the positive second. So 2 over 1 is just 2, and 2 squared is going to make that 4. If I put in a negative 1 instead, put in a negative 1, then it's 2 over 1 to the positive 1, and that makes our answer 2. Anything to the power of 0 is 1. Anything to the first is itself. And then 1/2 to the second power, 1/2 times 1/2 is going to be 1/4. What happens in this graph? Well, now at negative 2, we're up at 4. And at negative 1, we're at 2. Anything to the power of 0 is still 1. And now we're at a half and then a fourth. What happens is that whole table flipped if we're comparing it to the blue one. That instead of our graph going up from left to right and starting to grow, our graph goes down from left to right. We can call that a reflection over the y-axis. Oops, undo. I want my pen on here, where again we're going to start to grow. Let's get that one in there too. As we go this way, and then it's going to get closer and closer to the x-axis as we go that way. So that was 1/2 to the x power. A reflection over the y-axis is what that looks like, right? Our graph is decreasing instead of our graph increasing, but the shape is the same. It still has that horizontal asymptote and still crosses the y-axis at 1. Okay, so now you can probably imagine what's going to happen with this next guy. 1/2 to the negative second is going to be 3 over 1 to the positive second. So 3 over 1, which is 3, squared is going to make this 9. And then 3 to the first is going to be 3. Anything to the power of 0 is 1. And then we're going to get a third here, and then 1/9 here. So at negative 2, we're up at 9. And then we're at 3, and then 1 again, and then a third. And then basically this is the mirror image of the red one. And, this is harder than it looks to try to get this in one fell swoop and make it look... I'm trying. 3 times a charm, maybe. Maybe that's good enough. All right, so 1/3 to the x power here. Again, just a mirror image of that one that we had in red where our graph was decreasing instead of increasing. And the smaller, in fact, that fraction gets, so a half we see is a little steeper. The smaller that fraction gets, the steeper we're going to see it on that side. So it's going to increase faster, or decrease faster, where the other ones increase faster. Okay? So what are some characteristics that we should recognize and sort of have in our head in place about exponential functions? In the same way, again, when you see a quadratic or you hear the word quadratic, you kind of know. Quadratic means x squared. It's going to make a parabola, goes left and right forever. It's going to have some min or max, right? These things that we know about parabolas, for example, we should kind of know about exponential functions as well. So the domain, as I mentioned before, unrestricted, right? All of these graphs go left and right forever because there's no restriction on what we can plug in for x. So domain was x's. We can plug whatever we want in for x. So every single domain was from -infinity to infinity. Or we could say all real numbers. We can plug whatever we want in for x in an exponential function. It's going to spit out a value for y. But the range was restricted, right? The y values were restricted here. These graphs were going to be approaching the x-axis, but they were never going to get there. So we are going to be approaching 0, but since we couldn't get there, we're going to keep a parenthesis on the 0, and then we were going to go up forever toward positive infinity. So the range is from 0 to infinity, not including the 0. So since these couldn't get to the x-axis, none of them had an x-intercept. There will not be an x-intercept. And because anything raised to the power of 0 was 1, every time we put a 0 in for x, we got 1 for a y value. Every single one of these graphs crossed the y axis at 0, 1. They all had a y-intercept at 0, 1. And then all of these graphs had a horizontal asymptote. They all had a horizontal asymptote, or barrier, at the x-axis, which is where y is equal to 0, at the equation y equals 0. Now, the only difference in the graphs that we looked at above were that the first two were increasing graphs, and that the next two were decreasing graphs, which should make sense when you think about the base of the exponent. So again, here the base of the exponent was 2, and what happened was we were doubling our number. 1/4 times 2 is a half, times 2 is 1, times 2 is 2, times 2 is 4. When our base was 3, we were tripling. So a 9th times 3 is the tripling that would be a third, and then times 3 is 1, times 3 is 3, times 3 is 9, and then so we saw these numbers getting bigger because we were doubling, or getting even bigger because we were tripling. What's happening here is our base of a half means our numbers are getting cut in half every time. So 4 times a half, 4 cut in half would be 2. Times a half or cut in half would be 1. Times a half or cut in half would be a half. And so these numbers were getting smaller. And the same thing here, they're just getting smaller faster. And so when our base is bigger than 1, we see a graph that increases from left to right, and we call that exponential growth. And when our base is, I don't want to say less than 1 because the negatives are a transformation, but if there's some fractional value between 0 and 1, so some fractional value between 0 and 1, like the half and the third are, then you're going to see your values getting cut in half, or cut in a third, or cut in a fourth. They're going to be decreasing, and so we call those graphs exponential decay. All right, so when our base b was bigger than 1, that was like the red and the blue that we had up there, then the graph is increasing. The y values increase, and so we call those graphs, or we classify those as what we call exponential growth. Okay, and then when our base is some fractional value between 0 and 1, so not any fraction, like 5/4, for instance, that's bigger than 1, that's going to be growth. But if we had, let's say, 3/4, if we cut our number by 3/4 every time, then our numbers are going to decrease, the y values would decrease, and so we would have a decreasing graph, and we would classify that as exponential decay. Now, not every increasing graph is growth and not every decreasing graph is decay, because Again, transformations can alter some of these things, but in general, like the parent versions of these increase with growth and decrease with decay. Okay, so this is like the parent. These are the 2 to the x or 1/2 to the x. You can sort of consider the parent of exponential growth and exponential decay, but of course transformations do apply. So let's talk about those. The same transformation rules that we talked about in our function unit and have mentioned several times throughout our modules still apply. So we have, remember, A, H, and K that affect the width, or whether we translate left or right, or reflect or translate up or down. Same stuff will happen here. So our basic form, like our parent form, is y equals b to the x. The standard form is going to be y equals a times b to the x minus h power, and then plus k. So we still have our parent function in there, right? You still have b to the x power. But now we have something that we could multiply out here, add or subtract here, and add or subtract here, and those three things affect the graph. A is going to affect the width of the graph, and whether or not the graph is going to reflect. H tells us if our graph is going to shift left or right, so H is for the horizontal shift. And then K tells us if our graph is going to go up or down. It's that vertical shift. Okay? So if we are looking at 2 to the x as our parent, what's going to happen if we incorporate this plus 3 and this minus 1? So if 2 to the x is our parent, then this plus 3 is going to make the graph go to the left 3, and this minus 1 is going to make the graph go down 1. And if you weren't sure, remember, we have Desmos that does graph for us. So here's y equals 2 to the x power. That's what we just put on paper a few minutes ago. If I put a plus 3 into that exponent, let's put a plus 3 up here, then we can see our graph went to the left. And it's a little hard to see them simultaneously, so let's put a second one in here. Y equals 2 raised to the x plus 3, no, plus, I can't type. 3, there we go. So it's a little harder to see than the parabola shift, but it has definitely gone to the left, okay? And then what happens if we put a minus 1 afterward? Again, we can check. We can see this one's a little easier to visualize. Come on. Minus 1. There we go. A graph that is shifted down. It's below the one that's in red. Okay? Now here we've got a whole bunch of transformations. First, we have a negative, and that negative is going to make our graph reflect over the x-axis. Reflects over the x-axis. And so if our original was here, we would see something that would be reflected over the x. It'd be upside down. And then we have the 1/3, which is going to vertically compress the graph. So the 1/3 is a vertical compression. And that, it's like it slows down the movement of the graph, which makes sense, right? Your 2 to the x, we know, doubles our number. So if you have 2 to the x and you double every time you increase your x by 1, well, now if we have to take that result and multiply it by 1/3, it's going to slow down the double, right? Well, we're going to double it, but then we're going to cut it by 1/3. So it's going to compress that graph. And then we have the minus 2, and the minus 2 there is going to make the graph go to the right 2. Okay? And then here, we've got a negative in the exponent. Now, we already know the negative exponent rule. If we have a 2 to the negative first, then it's 1 over 2 to the positive first. We saw this on the front of the note, or the other side of the note paper here, that was growth versus decay. Well, if we look at the growth versus decay, the decay, it's just a reflection over the y-axis. So that negative is reflecting our graph over the y-axis. So that reflects over the y-axis. I'm not sure why I chose that one first, but this guy is going to be a vertical stretch of the graph. It's going to make the graph, it's going to stretch out or increase the movement of the graph. So again, 2 to the x, we double, right? If now, after we double, we multiply by 3, it's going to be triple the double. So it's going to make that graph grow even faster. It's going to stretch it out. And then lastly, we've got this plus 4, which makes everything go up 4 units. Okay, so same transformations that we've talked about before. All right, let's look at this, another version of an exponential function where we bring back e. So we've talked about e before as the base of our natural logarithm, and we'll see more of this with some applications in a future section. A little more about e since we didn't technically put it in the notes before. So e is called Euler's number. You might be thinking, where is she getting that word? But it looks like Euler. It's technically pronounced Euler. Leonhard Euler is the man that discovered this number. Again, it's often used as the base of an exponential function, particularly in the finance world. So remember, though it's just an irrational number, it's like pi, okay? It's an irrational number, meaning it's a non-repeating, non-terminating decimal, like pi is about 3.14159, but we just say, oh, it's about 3.14. So remember, e is approximately 2.71828. The decimal goes on forever, but we just sort of say, okay, it's about 2.72, okay? So kind of try to remember, put that in the memory bank. E is about 2.72. Again, often used as the base of an exponential function. So let's look at y equals e to the x, so an exponential function with the base of e. Again, we have technology that graphs, but this should make sense, okay? If we put in a -2, e to the -2nd, or 1 over e to the +2nd, it's going to get you the same thing. Let's go ahead and put this in the calculator. E raised to the -2nd is going to be about 0.14-ish. We're not even going to be able to see that on the graph, so it doesn't matter. Put in a -1, and we have about 0.4. Just going to round that. Anything to the power of 0 is 1. E to the first is itself, so there's about 2.72. I guess I don't have to be so squishy. Sorry, about 2.72. And then e squared is going to be about 7.4. And what's going to happen on this picture, again, should make sense. So if we have 2.72 as our base of our exponent, that's what we're saying here, then that base is bigger than 1. What we should see is exponential growth. And that, in fact, is what's going to happen here. So at -2, we're up a little bit. -1, we're up a little higher. Anything to the power of 0 is 1. And then we're at 2.72-ish here. And then at 2, we're at 3, 6, 7. Wait. 3, 6, 7. So like around here. And again, there it is. The same picture we saw on the front. It's just another version of exponential growth, where we're going to have a horizontal asymptote here in the graph, and then we're just going to grow really fast. It's a base of 2.7, so that steepness would be right in between the 2 and the 3 that we graphed on the other side of the note page, okay? And just for good practice, this is an increasing graph. It is going up from left to right, and it is growth because our base it's about 2.72. It's about 2.72, which is definitely bigger than 1. Domain, everything from -infinity to infinity can be plugged in for x and it will produce a y. Range is getting closer to 0 and then going up forever. None, no x-intercept, doesn't cross the x-axis, there's a barrier there. Has a y-intercept at 1, just like all the other exponential functions did. Asymptote at y equals 0. And then our end behaviors. Well, as we follow this end of the graph here, or at the same time the graph is going up, it's also if we were following the graph to the, I'm on my eraser, I'm so sorry. If we were following this way to the right, that's what this says. On the x-axis toward infinity, follow the right. Go to the right end of the graph where the y value is going. They are headed up toward positive infinity. Get rid of all this mess that I just put on my paper. Okay, so as we follow the right end of the graph, the y values are going up. Now on the left end over here, if we go to this left end of the graph, where are these y values going? Well, these y values, right, Where are they going? This direction. We're getting smaller and smaller and smaller. We're getting closer and closer to that asymptote. So remember, when you have a horizontal asymptote in your graph, the ends approach that horizontal asymptote. So the y values, they were getting closer and closer to 0. Okay, trying to get there to 0. And the transformation rules that we talked about a second ago, those would still apply to a base of e. Base of e is like any other exponential growth. I just wanted to throw it in there so it doesn't freak you out if you see it later. Okay? Now, just to sketch or use the transformation rules, the purpose of knowing those, remember, so that we can try to sketch and have a visual of what's happening here without using so much technology. But of course, we can always go to Desmos to make a graph too. But let's see what we can do without technology before we go to it. So, for example, if we had y equals negative 5 to the x minus 1 minus 2, you should be able to see the parent function in there. So this is all based off of y equals 5 to the x. And y equals 5 to the x would be just like 2 to the x or 3 to the x. That's the picture. Now, if that now has a negative and a minus 1 and a minus 2, what are the effects? Well, our 5 to the x would be reflected over the x-axis, so it's going to be upside down. Reflected over the x-axis. And then there's a minus 1 in the exponent, which is making our graph go to the right 1. And then there's a minus 2 after our exponent there, after our function, which is going to make the graph shift down 2. Okay? So let's take care of that reflection first. So normally, our horizontal asymptote would be here, and our graph would be here. But we want to reflect that over the x-axis. So right now, our graph is going to be, instead of crossing at positive 1, it would be crossing at negative 1, and it would be approaching the x-axis here, and it would be growing in this direction. So there's where we're at so far. That's just the reflection. Okay? Now, if we need to take that graph and make it go to the right 1, so to the right 1, well, our horizontal asymptote's not going to shift if we try to go left or right, but we want to take this whole graph to the right 1. The easiest thing to take would be that point where it crosses the y-axis. So what I'm going to do is take that point and put it here. So instead of this point being here, I'm going to take it to the right 1, which would be here. And then everything's going to shift down 2. So now our horizontal asymptote has to move down 2, and this point has to move down 2. So if we shift all of that, instead of being at 0, we're down 2. So horizontal asymptote's going to move to negative 2. And we had been crossing here, right? And then we shifted that down, or right 1 and then down 2 from there. So there's our new point of reference. And then we're just going to sketch this approaching the asymptote and then growing in this direction. So there's a sketch. Okay, now let's just verify that we got this sort of going in the right direction here. So y equals negative 5 raised to the x minus 1 power. I don't know what, I guess my fingers are too big for this little keyboard. All right, and then after the exponent, a minus 2, and that appears to be what we've graphed. And yeah, this looks about right. Okay, so it's got the graph crossing the x-axis at negative 2.2, and my branch is a little off here, but it was basically right. So I'm just going to scooch that up a little bit. Let me just try this again. So this was here, and this is difficult. Pen slides around, or whatever, something like that. Okay, so this graph technically is a weird case. Okay, if we were reading this graph left to right, it's definitely decreasing. These values left to right go down. But remember, the what determines if the graph is growth or decay is the base of the exponent. So originally, this parent function 5 to the x was a growth function. The negative is what flipped it over and made it decrease. So what we call this is negative growth. It is growing in the negative direction. So it's still growth, because the base is 5, and that's bigger than 1. Okay, the negative doesn't go with the base there. The base is just 5. So what we're looking at to determine if it's growth or decay is the parent. Look at the parent without all those transformations in there. Okay, now this still has an infinite domain. I could still plug whatever I want in there for x, but the range has shifted. So instead of approaching 0 and going up forever, this graph goes down forever, and then it's capped there at -2. So this goes down forever toward negative infinity, and then it's approaching -2, and it's not going to get to that asymptote at -2, so we want to keep a parenthesis on that. The x-intercept. So 2 things about the x-intercept. It's crossing the x-axis this time, because, oh sorry, not crossing that. I don't know what I was thinking. Getting ahead of myself. It does cross the y-axis, not at an exact point. It still doesn't cross the x-axis, so we can see that barrier shifted our graph down, so it's still not going to cross. It's possible that the graph could cross, right? If I took this graph and I shifted it up 3, 4, 5 units, it's gonna cross the x-axis. If we wanted to calculate exactly where the x-intercept was, remember you could always put in a 0 in for y to solve, which wouldn't be very much fun, or you can use Desmos and find that specific point. The y-intercept, that's the one we already got from Desmos. So from Desmos we saw that it was crossing at 0 and -2.2. That was from Desmos. Okay, but again, if you wanted to put in a 0 for x and solve by hand, you could figure that out. So this was at 0 and -2.2. And then the asymptote will always be at the value of k. So think about our parent, right, b to the x, there's nothing being added or subtracted out here. There is nothing being added or subtracted for k, and so it was at 0. Well, if we add a 2, let's say, then our graph would go up 2, and so would the horizontal asymptote. If we subtracted 2 like we did in this case, then everything shifts down 2, and so does our horizontal asymptote. So the horizontal asymptote will always be the value of k. So in this case, it's y equals -2. And then the end behaviors. If we go to, I'm missing an x here. If we go to the right end of this graph, these y values are headed down forever toward -infinity. And if we go to the, I'm so sorry. If we go to the other end of the graph, the left end of the graph, these y values are getting closer and closer to that asymptote. So on the left end here, we're approaching -2, the asymptote. Okay? So basics of graphing, all right? I just want to make sure we really understand and can recognize exponential growth versus exponential decay versus maybe something that isn't even exponential. So looking at the first graph, hopefully you can see that this is an exponential growth function. Maintains the shape of our exponentials that we've been graphing, increasing from left to right, growth. Okay. The next one doesn't have an asymptote at all. No asymptote in there. Doesn't maintain the shape of our exponential growth or decay functions. So hopefully you can see that this is neither. And we just finished a unit on polynomials. Hopefully you recognize that as a polynomial function with an odd degree. Whereas the last one here, we have got an asymptote and the graph is decreasing, so this is likely a exponential decay function. So exponential decay, exponential growth. And then here, got a list of actual equations for functions. And again, you should be able to determine by looking at it, do we have exponential growth, do we have exponential decay, or is it neither? Well, the first one is neither, because this is not a variable exponent. Again, that's a cubic function, that's a polynomial function, so that's neither. This has a variable exponent, so I know it's exponential. The question is it growth or decay? So this is exponential, And because the base is a fractional value between 0 and 1, right? 0.75, think about it as a percent, okay? The 2 to the x, that'd be like 200% there. Our number is going to be 200% of what it was the next time we multiply, right? If our decimal in there is a 0.75, that's like a 75%, we're only going to have 75% of what we had the next time we go down. So we're going to be cutting that graph by 3/4 every time, by 75%. So this is going to be exponential decay. And then the next one, again, exponential. We've got a variable exponent here. 1/3 means we're only going to have 1/3 of our number every time we multiply down or input the next x value. The y value gets cut by a third. So again, that's going to be exponential decay. Next one is, again, exponential, because we got the variable exponent. This base is bigger than 1. We're going to have 5.3 times our number every time we move. So that's going to be exponential growth. And then the next one, we better recognize this is a linear function, not exponential. That's a neither. And then the last one is exponential. We've got the variable exponent, base of 2. We already saw that is going to be doubling our number every time. That's going to be exponential growth. Okay, so those are your basics of exponential functions, transformation rules that we've talked about before, being able to distinguish between growth and decay. Hopefully you've got enough to work on your assignment there, and then we'll, in our next topic, look at some applications of these functions. But for now, that should be good to get you going. As always, though, if you need some extra help or clarification, then just reach out. All right, guys, take care.